Hi everyone, myself Jyoti Prasad from RMD Engineering College. Now I am going to discuss about successive approximation ADC. So earlier we have seen flash type ADC in the earlier video. So now I am going to discuss about the successive approximation type ADC. So this is also a direct type ADC. So where we are comparing the analog input VA with where we are comparing the analog input VA with another voltage, which is VD. So here in successive approximation ADC, we are using DAC also. So here we have majorly three components in successive approximation type ADC. One comparator, op-amp comparator, one successive approximation register SAR, we will call short as SAR, and the third one is a DAC, DAC. So the comparator output it drives the successive approximation register, which will have the another input as a clock, and where it will start commencing the SAR start commencing after issuing the start signal, and at the end of the conversion, it will issues an end of conversion signal. So successive approximation output will drive output is SAR output is a digits. So these digits will be given as an input to DAC, where the DAC will take the input digits digital as an input and converts to analog value, and again it will give to the input one of the input of comparator. So where this VA and VD will compare, and it will repeat this process in cycles. For example, an 8-bit comparator requires 8 clock periods to, that means 8 cycles will be rotated. So after that end of that 8 cycles, we will get these are the equivalent digital value for an analog value what we are providing as an input. For this VA input, analog input, we'll find out the digital representation. So let us see the operation of successive approximation register. So here, like I said, the start of when the arrival of the start signal SAR sets to MSB with D1 1, and all other bits sets to 0. So here we see this is a D1 MSB, the LSB is the last one D7, D8. Okay. So here the first bit MSB will be set as 1, the remaining all the bits is set as to 0. The code is converted to analog with the help of digital to analog converter. For example, see the comparator operation. First, the output VD of DAC is compared with VA. So, like we have seen, see here for the reference, we have the circuit in the bottom of the slide. Here, VA is compared with the VD. VD, which is the digital, VG is the analog output which is coming from DAC. That's why DAC. D for DAC. This voltage which is coming out of the DAC will compare with VA. So if the VA, whatever the main input which we need to convert into digital, that is greater than VD, then the MSB, whatever here we have the MSB here, this will be left as one as it is. Then the next LSB will make it as one. So then it will make it as 1100 and 0000, like that it will do. So if VA is less than VD, which will be the last conversion, then the last or in between also we can see this type of repetition combination. The MSB, if VA is less than VD at one case, then the MSB is reset to 0, and we will go to the next LSB. So for example, if this one is 0 means instead of 1 we will make it as 0, the next one we are going to make it as 1. So likewise we will do the operation if VA is less than VD. So this step will follow, this the above two steps will be followed until all subsequent bits, I mean, if we say 8 bit, all 8 bits completed means 8 cycles completed. Until that, it will repeat whenever the DAC output crosses VA. I mean, VD is greater than VA. I mean, VA is less than VD. The comparator changes its states and it will issues end of conversion. Like I said, I will explain with respect to operation with a truth table. See, I am taking a voltage VA, so which I want to convert into digital. So for our understanding purpose, say this is the digital equivalent of this voltage VA, for example 10 volts or 15 volts. So this one is not known to the machine. So the ADC. So we know for our reference we are keeping here. Initially, like I said, whenever the SCR is initiated, the MSB will be 1 here, as the remaining bits, all bits will be 0. So then the output will VA is greater than, in this situation VA is greater than VD, greater than VD. So the output will be 1. So in the next cycle, the next LSB will be the next LSB will become 1. So then this one. Okay. So now it will compare VA with VD. So you see here VA, but double ones are there in the first two position. So 0 is there. So here also double one, 0 is there. So if we see 3 bits, we are not able to tell. Then we will check for fourth bit. 101101. So here double one double zero. So definitely VA is a greater one. So VA greater than VD will satisfy. So the output is 1. So the next MSB will be, the next bit will be 1. So already we have double one, so the next one we are made as 1. So now it will compare these first three or else first four with the VA. So again VA compared with VD. So if we compare VA with VD, see here first three ones are there here, but here 110. So that thing, but the VD is greater than here. So VA is less than VD will come here. So the second case of the comparator operation, then what it will happen, then the comparator output is 0. In the next cycle we will make this third bit as 0, the next bit we will make it as 1, as we have seen the statement in the earlier slide. So then, so here the first four bits is equal to the first four bits of VA, for our reference what we have taken in the first column. So then, so if we compare here first 5 bits, first 5 bits, so both are equal. If we go for sixth bit, then we will come to know that VA is greater than VD. So we have output 1, we have output 1. The first greater than case means the comparator output will become 1. So we will keep this one as it is and we will make the next step. So up to here 4 bits we have done here. So the first 4 bits as it is. So the next fifth bit we will make it as 1, as it is the fifth iteration. 1, 2, 3, 4, 5. Fifth iteration. The fifth bit we make it as 1. So now we will compare these five bits with the 5 bits of the VA value. So obviously it is VA is less than VD. VA is less than VD. So if we compare first 5 bits, so we will come to know that. So then the output of the comparator is 0. So what we should do, the fifth bit I will make it as 0. See here, the fifth bit I will make it as 0 and the next bit I will make it as 1. So now the next case, when we compare 6 bits, when I compare 6 bits, so VA is greater than VD only. VA is greater than or equal to case. I mean this is equal to case. So both are same. Here itself we can stop. We can't stop even though the value is same. See, 11101 1101 0100. So but this is equal case. So even though then the comparator output is 1, that means previous case, previous. So 1 will be there. So the one means we will keep it as it is, the next bit will make it as 1. So now less than case will come. So less than case means the output is 0. So in the next cycle we will make this bit as 0, the next bit as 1. So again less than case will come, output is 0. Then we will keep this bit as it is 0, the next bit make it as 1. There is no next bit. So that's why we will stop here. So the last value after 8 cycles, that is nothing but 8 plus 1 extra cycle. So the last value what we got is the equivalent representation of VA. So if we compare these two things, then it will be equal. But even though the same value came in the seventh cycle or sixth cycle, the 8 cycles has to be completed. So this is regarding successive approximation type ADC. So coming to this DAC, it requires, like I said, the highlight point is that it requires 8 pulses to establish accurate output regardless value of analog input. However, like I said, extra one cycle is there, right? This additional clock is needed to reinitialize the circuit. Thank you.